Okay, so hello everyone. Let's start it. So welcome everyone to join in today's Icon X talk. So I'm Yipeng Lu from Peking University, going to chair today's talk. Today it's our honor to have Professor Ashwin Seshia from University of Cambridge to give us a talk. Um, Let me give a quick introduction for Professor Seshia. Ashwin Seshia is a professor of microsystem technology at Cambridge University and institute chair professor in electrical engineering at IIT Bombay. He received his bachelor degree in IIT and master PhD degree from UC Berkeley. He has held visiting position at Stanford University, UC Berkeley, IIT, and also UCLA. His research interests including MEMS design, particularly in relation to sensors and the sensor system. Ashwin received 2018 HV Sensors Technical Achievement Award. He was appointed a distinguished director of HV Sensor Council for the period of 2020 and 22. Ashwin has acted in numerous service and leadership roles for MEMS, sensors, frequency control technical committee, and currently serving on the International Steering Committee for the HV MEMS conference, and is the co-general chair of HV MEMS 2026. So actually here, I will encourage everyone try to submit the abstract for the MEMS 2026 in Europe. He has previously served on the editorial board of JMM, attribute transaction on nanotechnology, attribute transaction on UFFC, and also attribute journal of MEMS. Ashwin is a chartered engineer, is a fellow of IOP, IET, and IEEE. Ashwin was elected as a fellow of Royal Academy of Engineering in 2023. Now, let's welcome Professor Ashwin Seshia. So Ashwin, I'm going to stop sharing and you can start anytime when you are ready.
Thank you, Professor Yipeng, for that very kind introduction. And thank you for having me here. So it's a pleasure to present to all of you on a topic that has been quite central to my own journey in the field of microelectromechanical systems. And I've shared this journey with a number of the panelists here, as well as a number of mentors, collaborators, students, postdocs, and other colleagues who have contributed immensely to this journey, which continues in a very interesting field. So I hope to give you a bit of a flavor for some of the journey I've been on and the path forward. All right, so in terms of the talk today, I want to start out by giving you a bit of a historical context for this topic, and then very briefly cover the basic principles of operation, some of the initial work that we did around device validation, and then dive into some applications, particularly in the context of precision measurements, with a view towards field deployment of the technologies that resulted. And then talk to you a little bit about other emerging transduction principles and give you a flavor for the potential for those and others that are emerging in this field. All right, so with that, what I'd like to start by saying is that, first of all, the field of precision measurements has a very long history, probably as long as, human civilization has wanted to measure physical phenomena and measure with increasing precision. But in terms of the particular area that I'm going to talk about in the area of micromachined resonators, I sort of see it as an evolution of technology that probably in itself is about a century and a half or so old. So this technology, as you see, deals with how tiny silicon beams resonating in a particular mode can be made sensitive to external measurands, and how you instrument that for various applications. But in many ways, the first versions of these at the macroscopic scale, as I said, were at sort of the end of the sort of 19th century or so, and then really started to emerge in terms of applications, real-world applications in the 1920s and 30s. So these were macroscopic, typically vibrating wire gauges. And then further development started to take it forward in the field of precision measurement. So for example, gravimetry, with the first instruments being reported in publications in the 1940s. We then see the advent of MEMS technology, but that's, again, part of the drive to miniaturization. And around that time, you also see a lot of work in quartz crystal technologies. This continues as an evolution, of the vibrating string gauges. In fact, vibrating string instruments continue to be used today. But you see work on quartz crystals emerging and then maturing for applications, for example, in force and pressure sensors. And while silicon MEMS starts to roll out with some key academic publications, key bits of work in industry around this time in the 80s, you start to see a lot of interest in driving towards precision measurements as well, using silicon vibrating beam technology. And when I did my PhD in the 90s, MEMS was still largely an academic subject. It's now really translated to industrial application. But it was around that time we had a lot of the early projects around inertial sensors and so forth, which are now quite commonplace in consumer, automotive, and other sectors. So you see that sort of move from research to translation, commercial development, and then push towards higher end applications for MEMS, and continuing research in exploring alternative transduction domains, all with a view towards trying to push towards the limits of measurement of physical phenomena around us. So this is the one publication I'll point to. This is from my advisor, my PhD advisor, Roger Howe, a mentor at UC Berkeley, where I did my PhD, and his work sort of was one of the key foundational pieces of work around surface micromachining and resonant beam sensors. So in his PhD thesis, what you see here is the surface micromachined structure that is made responsive to certain types of chemical signatures through a mass loading phenomena. And that results in a shift in frequency, and the sort of the key integration bit was, you have the circuitry also integrated on the same substrate to do the initial signal conditioning. So this was one of the landmark papers around the time in the field of resonant systems, and it was followed up with other papers. In fact, there's also work around that time in industry in bulk micromachine sensors and so forth. So you start to see, together with Kurt Peterson's e-paper on silicon as a mechanical material, a lot of activity that starts to catalyze this whole area. And so my own PhD was in the field of MEMS inertial sensors, particularly focusing around resonant output devices. And this is one of the papers in the Journal of MEMS, where we looked at integrating these vibrating double-ended tuning fork type structures that you see up in the schematic here, and maybe a little bit less clearly in the dye photos that are shown below. These were integrated with front-end oscillator circuits on the same substrate, the whole thing vacuum sealed to provide the vacuum ambient for the MEMS structures, allowing you to be able to do measurements of acceleration, in this case, time-varying acceleration responses was what we were looking at. And so that really is sort of the start of the journey. And, you know, at Cambridge, I initiated a number of projects that followed on. I had a particularly sort of a good collaborative partnership with a civil engineer at Cambridge, Kenichi Soga, who's now moved to UC Berkeley. And civil geotechnical engineers were interested in strain measurements in structures such as tunnels, bridges, and sort of other sorts of areas where, in fact, conventional vibrating wire gauges were used. And we kicked off a series of projects looking at MEMS-based strain gauges. And this was in the 2000s or so. And the idea here is, you know, with the double-ended tuning fork, as shown here, integrated with capacitive transduction, you're excited in one of these modes. And it turns out that these can be made extremely sensitive to axial forces. So if this is then mounted on a structure which is deforming, you can pick up very sensitive signatures of that deformation. And that was the idea. I'll get into this in a little bit, but the idea is very similar to a tuned, you know, a string musical instrument. So, of course, predating the vibrating wire strain gauges, there's been, of course, sort of the work around string musical instruments and so forth, where you know the observation clearly is that if you modulate the tension in the string, you change the frequency. So that is basically the very simple explanation of the physical phenomena here. But as you scale down the dimensions, you turn out to be incredibly sensitive. So your strain resolutions can be well into the nanostrain to picostrain sort of levels. And this can be achieved potentially at very low power levels, as I show later. So in terms of some early works, this is out of Joshua Lee's thesis. He was among some of my first PhD students. He had done actually an undergraduate degree at Cambridge and then continued on for a PhD. And this was one of the structures from his thesis. It's actually a charge sensor. But you know, it's sort of a proof of concept towards the strain gauge. The idea again here is you've got these two tines for double-ended tuning fork connected up to these electrodes, and these are driven capacitively, sensed capacitively as well. And you can apply tiny quantities of charge on a separate electrode that is pulling on this tuning fork axially. And as you do so, you change the frequency. And again, this can be modeled. The governing PDEs would then be solved. You know, you can start off with a simple model for a clamp beam, extend it to a tuning fork and so forth. And you'll find that, for example, a Rayleigh analysis for the natural frequency would give you something of an expression that looks like this. So an analytical expression where the natural frequency as a function of the axial force varies non-linearly. And if you plot that, you get something that looks like that. So a square root relationship over this range, and that range can be quite large. Now, you can linearize it over a small range over the unloaded condition, and it's pretty linear over that range. Basically, if this term is small, then you take the first term of the Taylor series expansion, so to speak. And so for the tuning fork, this is what the linearized expression is that you end up with. And what you see here is just from scaling arguments, you can make all of the dimensions scale uniformly as you miniaturize from a macroscopic vibrating wire to a miniaturized silicon beam, and all of those dimensions scale, then the sensitivity, the ratio of the change in frequency to the applied force, of course, scales up quite significantly. So that's the basis for the increased sensitivity as a force sensor or force gauge. And in the context of a charge sensor, as shown here, again, you can look at that responsivity to charge and the details in the paper. Again, you see that there is a enhanced sensitivity as you scale down in dimension. So that's one of the drivers for miniaturization. So this was actually tested in the paper. These are some of the raw responses as the voltage on that electrode that's pulling that structure axially is changed, and then you plot the frequency shift as a function of the applied inferred charge, and you get a relationship where the experiment and analytical solutions both go quadratically as to be expected. So that's sort of a basis, a starting point to try and understand this technology. And again, the roots are over a century old if you go back to connecting up to a vibrating wire type gauge. Now, some of the early devices, these surface micromachined polysilicon surface micromachine structures. You can, with MEMS, array up these devices for multi-axis measurements of temperature compensation and so forth. And this was work done in collaboration with the group at CNR in Italy, where this is now built into a platform to look at a MEMS-based extensometer. So as you pull on the two sides, axially, you modulate the strain in the MEMS, and that clearly is evidenced as these changing frequency response characteristics that are measured. Of course, as you can see here, this packaging is pretty crude, and that was worked on going forward to this paper, where we had the MEMS and CMOS co-packaged. So the front end CMOS had the oscillator circuits and did some temperature compensation as well. So there was a temperature compensated output, frequency output from these devices, all at a relatively low power level for that front end of about 3 microwatt. So the measurements from that are shown here. One of the advantages you see here is the very large dynamic range. So that comes with this principle, this frequency output principle. So you get the excellent resolutions well below the nanostrain, very high sensitivities, as I said, that enable that, but also the very high dynamic range with a very good linearity, even though the fundamental principle itself is nonlinear. But over this large range, strain range, you're still pretty linear. And this can be built into something like a load cell, which can measure down to a resolution of a sub-milligram in this particular paper published at Transducers. So Guangzhou reporting here a sub-milligram load cell just based on a MEMS strain gauge. All right, so the advantage is that you can start to enable energy harvesting, enable sensing. So this was one of the drivers in the infrastructure monitoring project that we had, because these sorts of sensors might be deployed on remote areas, bridges, tunnels, that sort of thing. So maybe scavenging energy that's in the ambient and then powering up these sensors would have been an interest. You've got a sensor continuously powered on, it needs to be operating at very low power levels. So that's some work that we did. Sejun Du, the PhD student, joined later on, led this work, and you can see Shudong as well on this paper. So this was a demonstration of a vibration-powered strain gauge, demonstrating the potential for these sorts of devices to be powered up by the ambient. And Professor Soga was interested in applications such as these. So there's a lot of deployments with the London Underground and other installations, and these sorts of sensors would then make their way into crack meters and so forth. So this is in fact a crack meter deployment as part of a European project, which one of the early generations of these MEMS strain gauges, where, in fact, the MEMS team went out in hard hats and all and deployed these for a limited duration of time. Okay, so in about 2009 or so, I had a project initiate with discussions initially, and then the funding kicked off in early 2010. And this was a project with BP. They were interested in monitoring carbon sequestration using downhole sensors, in particular downhole gravity sensors. And the idea is that in CO2 sequestration, you're pumping CO2 in the subsurface. There might be co-production involved. And the CO2 is displacing, in that co-production scenario, other fluids. So this is oil and gas, for instance. And there is a differing density contrast. So as that CO2 displaces other fluids, the density of the formation changes. And we're talking about, several hundreds of kilotons that are being pumped, over the duration of a monitoring period. That results in a very substantial change in, fluid densities in the subsurface. So if you had a bunch of sensors that could withstand those harsh conditions downhole and were deployed proximal enough, they were sensitive enough to pick up those large masses or changes in density in the formation, you can then infer how the CO2 is contained and how it changes over time. So as part of the monitoring mandate for carbon sequestration, gravity sensor deployment was of interest, and that was what the proposal was around, and that's what we kicked off. In fact, as I said, the work around vibrating string gravimeters wasn't new. So this is a paper also out of Cambridge, but it published in 1949, as you can see. And this is a vibrating string gravimeter that basically operates the same way, but is a macroscopic instrument. So again, there is a modulation of the tension in the string as the weight pulls down on it, and as the gravity force changes, you can then sense that as a change in frequency of the vibrating wire, change in its natural frequency. And this is compared to a pendulum gravimeter. So again, the natural frequency of pendulum, of course, was used for quite a long period of time for gravity measurements. And these are actual comparison measurements of both the types of gravity instruments side by side around that time, and reported in this paper, demonstrating one of the first early vibrating string gravimeters. So fast forward to our work. In fact, we started off with a very simple SOI MEMS process flow through MEMSCAP, as it was known at the time. And this allowed us to prototype some early devices. So this is very simple sort of simple few mask process. It's available to the MEMS community as a prototyping tool, and then you vacuum seal these sensors at a die level once they're back from the foundry. And so this is work that Shudong was involved in. And the first sorts of tests that he did, and there's a die photo inset, and the first set of tests was to mount this on a tilt platform and to record changes in the natural frequencies of the tuning forks connected to either side of the mass. So the idea here is that the two tuning fork strain gauges are connected up to this mass through, for example, a leverage scheme. And so as you orient the sensitive axis of this sensor relative to the vertical, different angles, orientations relative to the vertical, the component of the G-force acting on the sensitive axis, of course, changes. That can provide you the basis for a tilt measurement, assuming small g, of course, in this case is a constant. So you see that, and these are again results from the paper, a very nice sinusoidal curve that's traced, indicating a full measurement over the entire range of tilt angles. And over the sort of the small angle range, of course, you approximate sine theta as theta, you can extract a sort of a linearized response around that range. So these started to get tested in our laboratory side by side with other macroscopic instruments that were commercially available instruments at the time, some of the best instruments we could get our hands on. And some of the comparative measurements were very promising. These were again reported in this JMEMS paper led by Shudong, and showing that we had the basis for a seismometer type response in comparison to the much larger seismometer that was mounted nearby. And Shudong also did some very nice work around looking at the impact of nonlinearity that is inherent in these sorts of MEMS devices. So as many practitioners in the field will know, as you scale down the dimensions, you operate under vacuum conditions. High Q responses often imply that your devices can go nonlinear at very low drive levels. And in this work, Shudong looked at the impact of that on noise folding to the carrier. So you've got potentially a combination of effects where the nonlinear response can mediate that noise folding to the carrier, and thereby degrade the low frequency performance of these sensors. So this was studied through a combination of experiment and modeling, and also tying in some previous work from our group in the area of MEMS oscillators in this sort of area. So you can start to then look at optimum drive levels and that sort of thing, depending on the application of interest. So one of the limitations in our university lab was the fact that we were in a fairly noisy environment. There were other sort of instruments and work going on, a lot of human activity and road activity nearby. So we needed to go somewhere quieter to get rid of that sort of environmental noise. And one of the facilities we went out to was this facility in the south of France. So it's a facility that's built into a mountain. It's quite remote, and it's a repurposed facility. So you have to, in fact, travel more than 1 kilometer down a not so well lit tunnel like this, and it gets darker and darker as you go deeper and deeper, and you get into a small little cabin laboratory that looks like this. So we were both in hard hats, and this is us trying to figure out what was wrong with one of our circuit boards. Clearly not the best place to be doing that. But it, that whole week there and then subsequently at other facilities gave us a real insight into some of the limitations, because we were at least able to get rid of one of the ambient noise sources in the university environment. And it gave us insight into, for example, environmental effects that we published later on in JMEMS. So the impact of ambient fluctuations, environmental fluctuations, and their impact on the response of these devices. So these tuning forks are incredibly sensitive. They pick up not just the measurand, but they can be coupled into temperature variations and pressure variations that need to be compensated for, potentially compensated for at multiple levels. So you can talk about compensation at the material process level, at the sort of the device design level, at the circuit level, and then even beyond the front end circuits and sort of more compensation that can be done at the package level and so forth. So there are multiple levels, and this sort of study gave us an idea into some of those effects, and led us to being able to start to suddenly pick up interesting signatures that we didn't anticipate picking up when we went out to do some of our testing. So this was in one of our expeditions to the University of Bristol, where we are out at the basement laboratory in Bristol. They have a low noise laboratory. And while we were out there, in fact, this was, I think, an overnight record. As we were getting ready to go back into the lab, we heard the news of an earthquake in Mexico. And having just sort of thought we'd fix the instrument the previous evening, I think we went back, had a look at the data, and found signatures in the record of our MEMS instrument in Bristol. So this is, in fact, a time frequency plot showing that we picked up the P and S waves, and we then correlated it to the nearest geophysical monitoring station run by the British Geological Survey with a good correlation. What is interesting is that you pick up the low frequency signatures in this record, showing some of the benefits of the sort of the vibrating beam approach that allows that sort of sensitivity at those frequencies. And subsequently, we started to pick up a number of different signatures, teleseismic signatures, both small magnitude events more locally in the UK, and then other events like this one again, where you see in the time trace again the sort of the long period oscillations that are picked up with the MEMS instrument here. So that is a demonstration of sensitivity. We then went out to a low noise site in Scotland, where we acquired some data to give us some insight on the stability of the instrument. And what we see here is stability is approaching 10 nanoG at an integration time of about 1,000 seconds. And this then allows you to start to do measurements where you can track earth tides. So this is a classic measurement where you let the instrument record for a period of a number of days, and then you track the variations in small g due to earth tides and so on and so forth. So this collectively started to then set the basis for fairly sophisticated instruments and measurements that can be done. And then in the university as well, we work together with companies deploying instruments, borehole seismic, for instance, to integrate our MEMS sensors instead of the more conventional macroscopic seismometer, the geophones in those instruments. And this was a very instructive, again, field deployment of the technology in an early stage of the MEMS sensor itself. It gave us a lot of lessons and learnings that we were able to incorporate into future evolutions. Okay, so that's an example. All this has now translated as of several years ago to silicon microgravity, which is now selling these instruments. I'm going to now fast forward to a topic which is still more academic in coupled resonators and mode localized sensing, but it's also generated a lot of interest in the MEMS community and continues to remain an active area of research. And one of the questions that was posed, again, this work was initiated when one of my students, Pradyumna, who's one of the co-authors of this paper here, joined the group around 2007 or so, was to ask the question as to, okay, we've been looking at single resonators or two decoupled resonators. Are there physical phenomena that emerge, collective phenomena that emerge when you couple resonators together, and they provide you the basis for an alternative transduction approach that provides a completely different way of measurement that has advantages as well that might go along with it. So it's part of a bigger question in MEMS as well, as you try to look at collective phenomena that you can exploit across arrays and so forth. So this is one of those phenomena that we looked at in some detail. So this was work that had its origins in those questions, but we also had a colleague in the engineering department, Jim Woodhouse, who had worked on some of the earliest measurements of vibration mode localization at a macroscopic level. And through this discussions, we evolved a principle that is dubbed as mode localized sensing. And the basis can be explained simply by looking at a schematic of two coupled resonators. Of course, the principle extends to a large array, but in a set of two coupled resonators that are nearly identical and weakly coupled, we consider what might happen if we have a perturbation in the mass or the stiffness in one of the resonators relative to the other. The analogy is to coupled pendula, where we move from a symmetric system where the mode shapes are symmetric to an asymmetric system where we change one of the parameters, for example, the length of one of the pendula. And there you, of course, then end up with these asymmetric mode shapes. And this principle of vibration mode localization at that time was well established at the macroscopic scale, but the earliest measurements were being done on miniaturized MEMS devices, is an outcome that of this sort of question to ask as to what alternative transduction approach we could leverage that might be sensitive to the asymmetry in two coupled resonators. So it's a phenomena where you genuinely exploit the fact that you have a combination that emerges due to the coupling across multiple structures. And that's also evidence, again, there were a bunch of studies numerically, analytically, and then through experiment that were done. So numerically, this can be studied as shown here in the context of two coupled beams, where you perturb, say, one of the dimensions of one of the beams. It can be looked at analytically. So one of the sister phenomena is that of eigenvalue curve varying, which had been studied quite a bit even at the MEMS scale around that time. And this is all, at this point, the system is entirely linear, and you can come up with closed form expressions, especially in the context of a simple case of two coupled resonators, to describe how the eigenvalues in the system change as a function of the disorder parameter. So this can be the stiffness of one of the resonators relative to the other, for instance, in this particular case. And so one of the things that emerges as well is that as you change the strength of the coupling, you make the coupling weaker, you end up with more drastic localization. You also end up with these, steeper wearing plots that emerge. This is sort of a pointer towards how you might tune the sensitivity in these systems. So to generate that very weak coupling, we looked at systems which were electrostatically coupled. So the coupling spring here was dominated by the electrical coupling between two double-ended tuning fork resonators. And we can change the stiffness of one of the resonators relative to the other by simply changing a voltage, because this electrostatic force is nonlinear. You have a voltage-dependent spring term that emerges as you change the potential on a gate electrode relative to the resonator, one of the resonators. And you can use that to controllably change the perturbation on that resonator relative to the other one. So the initial measurements were all done using swept frequency measurements, as shown here, using a network analyzer. And the frequency response is recorded. This is an example of an experimentally recorded veering plot, which Pradyumna at the time recorded. So one of the first sorts of records of this sort of mode swap that you see that is associated with the veering phenomena, and an experimentally mapped out zoom in of that veering zone. Okay, so in terms of sort of a perturbation-based approach used to look at calculating a change in eigenstate relative to a change in stiffness in one of the resonators, this shows to first order a linear proportionality to the change in stiffness. So that change in stiffness, for example, can arise due to force, axial force modulation on one of those resonators relative to the other one. Compared to a frequency shift, which is the classical approach, which I talked about earlier, you'll find that a comparison in the sort of the fractional sensitivities associated with both approaches is related to the nominal spring constant divided by the coupling spring constant. So the weaker that coupling spring is, for example, if it's generated using those electrostatic coupling type effects, you can tune it down to be very weak. You can come up with a significant relative enhancement in sensitivity. And so these measurements can be done. So this is an example device that was tested. Again, same swept frequency measurement setup. In this case, these are the records, the transmission records from that measurement, as the voltage on the side gate on one of the resonators is varied. And so you perturb the stiffness on that resonator relative to the other, and you can see qualitatively the changes quite clearly. These can be then mapped into specific values. So the ratio of amplitudes acts as a proxy for the eigenstate, and you can start to come up with a more quantitative measurement as shown here, and then compare this to theory. And so this starts to then provide the basis for some of the theoretical predictions, also some of the assertions around the relative enhancements in fractional sensitivity using the vibration mode localization approach, where you're measuring a ratio of amplitudes of the two resonators operating at a specific condition, a specific resonant mode relative to the resonant frequency shifts in that mode. And this is for the exact same stimuli. But the greater benefit was the potential for what we saw as passive environmental immunity. So the idea here is this transduction principle is sensitive only to the break in symmetry in the two resonators. So if there's no break in symmetry and both of those resonators respond identically to an environmental effect, such as temperature, for instance, because they're both made out of the same materials, they're co-located on the chip, etc. So you would expect them to behave quite similarly. You would expect, as a result, no break in symmetry due to environmental effects, and therefore no change in eigenstate. While if you have a measurand that couples in very specifically, for example, to a specific change in stiffness in one of the resonators and not the other, then you have a change in the eigenstate, and that then is a selective recorded change to the measurand, as opposed to be compensated for due to temperature and other effects. So in theory, that's all very nice. And some initial measurements showed that there was some of the basis for that. So you could see very little change where you changed temperature and pressure, while the frequency described a bigger effect. Now, this was all verified much later on, where you had a much better setup to locally control the temperature and look at changes in frequencies and amplitude ratios. So this was, again, temperatures changed here. The amplitude ratio is a function of stiffness perturbation. And you see the curves broadly lining up on top of each other, showing that, qualitatively, you don't see a huge change in response across this temperature range, and there's no compensation applied here. So it's just passive. While for the frequency shifts in the same device, you see a very clear difference in the responses that are measured for both the in-phase and the anti-phase mode. And this paper goes in a lot more detail. So, for example, starts to look at how you compare with relative differential frequency measurements. The benefit, of course, with something that's entirely passive is that you don't consume additional energy to run the compensation if you could do it all passively. Of course, there are limitations, and this again paper goes into some of the limitations that arise. If you have to compensate further, you get a first order compensation inherently to a degree, and there are further levels of compensation that may be required depending on the application. So Pradyumna demonstrated this mass sensor, again, using a set of coupled structures. This is out of one of the papers that he published, demonstrating the proof of principle as a mass sensor with electrically tunable sensitivity, because you tune the coupling between the resonators, and that gives you tunable sensitivity as well. Chen Zhou from my group later demonstrated a closed loop operation for these sensors. And the idea was to close the loop on one of the resonators using the standard oscillator architecture, and then record the amplitudes of response from the two coupled resonators, and then do a ratiometric readout to look at the response. So this is a comparison in that paper, that JMEMS paper, of the fairly tedious open loop swept frequency responses as compared to the closed loop responses, and allow you to do the real-time tracking of any changes in measurand here, dialed in by changing in the voltages to tune the electrostatic spring on one of the resonators relative to the other, and that changes the frequency, that changes also the amplitude ratio, and we get that real-time tracking. Milind showed that we could do this in the same device. We could combine, of course, both amplitude ratio measurements and frequency variation measurements in the same structure, potentially providing you the benefits of both worlds. So the ability to do very high resolution, short integration time measurements, together with the ability to get the passive immunity to common mode effects, and therefore this is all done without compensation. So you see that there's that improvement in the amplitude ratio at larger integration times because of that built-in passive immunity. So this can be combined to both devices. Hemin joined my group around that time, having in fact worked on his PhD on this topic, and then did some very nice work in terms of really pushing the limits on sensitivity. So as we looked at earlier, as you decrease the coupling between the resonators, you get an enhancement in the sensitivity arising from this approach. How far can you push it? If you push it too far, then of course with swept frequency measurements, you can't delineate the responses because you have modal overlap. So how do you extend this principle to the case when you've got modal overlap? And Hemin in this paper showed that this gets you, an extension to that regime with some caveats in terms of how you interpret the measurements, but you do get gains in terms of sensitivity. And in the closed loop readout scheme, this is something that could be implemented. Measurand around the same time also looked at pushing to the nonlinear regime, and so extending the ability to do ratiometric amplitude ratiometric measurements while moving into the nonlinear regime. So this combined modeling and experiment to show that the amplitude ratiometric scheme could be extended in the nonlinear regime, potentially with gains as well with the amplitude measurements, and specifically also focusing on particular operating points where those gains are possible. And so moving forward, all of this was integrated into work to demonstrate a highly sensitive accelerometer. And so this was work that was published by Hemin, looking at putting this all together and all of these insights. So insights that were derived from the various studies I've talked about, also looking at multiple modes that might be of interest, etc. And this allowed these sorts of measurements with Allen deviation now down to 75 nanoG, picking up microseismic background. And Measurand also recorded a tiny seismic event, not a very large magnitude one, but this was one of the small ones that occasionally crop up in the UK. So now published at Transducers, indicating that these sorts of approaches can be applied to those sorts of higher sensitivity precision measurements as well. So moving forward, in fact, I would say this is just one example of a whole class of techniques that can be based around the dynamics of MEMS resonators. And we've, as a group, done some work in this area. So one of the other effects that is of interest is the control and modulation of nonlinear effects, and how you can engineer these for sensing applications. So there are a number of different contexts where you may want to look at enhanced sensitivity, or in terms of energy efficiency, or in terms of reliability. And by specifically engineering these phenomena, you might be able to open up new approaches that allow you to gain one or more of these benefits. So nonlinear effects, as I said, are quite readily evidenced in MEMS and more so in NEMS devices. And you have to deal with them in any case from a modeling perspective. So to be able to leverage them for specific application, has been of interest to the community for now for some time. And the other advantage is that there is an electrical tuning knob, which is quite different to what you have at a more macroscopic scale. where these are often built-in phenomena which are not tunable. Well, at the MEM scale with electrostatic fields and so forth, there is a degree, in fact, often a high degree of tunability on these effects. So Xin Zhao, who's also here today, has done some really excellent work in this area, and is really leading the way in some of the new emerging techniques in this field. So I'm going to summarize. I'm coming to the end of my time. So as I said, this is a journey, and not just for me, but for this community as a whole, and has a history almost as long as MEM. But I see this as an evolution of a much larger picture where there's been a push towards, precision measurements and other metrics of interest for the community, for the instrumentation and measurement community as a whole. And so an evolution that traces at least as far back as, some of the precision vibrating string instruments go. And there are, lots of very interesting physical principles that are emerging. So we talk, the basis, the starting point being the classical approach based on, for example, a natural frequency modulation in silicon beam resonators, but that can be extended. For example, mode localized sensing and coupled resonators. And there's a lot of active research that's happening in this area as we speak, with Hemin and others, and Shudong leading the way in that. And there is a lot of other principles that are also emerging. So a lot of very exciting work that's happening with a lot of the panelists here really leading the way in this area. So with that, I will stop. There are many folks to thank for this journey, and I will not be able to read the entire very long list of contributors, but it's been a great pleasure, and it's been a privilege to work with outstanding group of collaborators, mentors, PhD students, and postdoctoral researchers over the years. So thank you all. That brings me to the end. And before I wrap up, I'd like to invite all of you to the IEEE MEMS conference in Salzburg in January. So as Professor Liu mentioned, I'm one of the co-chairs, and we're really looking forward to your contributions at this conference. It's going to be an exciting conference, a great venue. For those of you who've never been to Salzburg, it's one of the best venues I've ever been to, and really welcome you all to contribute and engage with the conference. We've got some exciting programs planned. Thank you all.
Okay, thank you, Ashwin. Thanks a lot for the fantastic talk. And just to remind everyone, I think the abstract will be due normally in September, right, for the MEMS 26.
Yes, it's in September. Yeah.
So probably students should already start preparing. So, okay, yeah, thanks. Yeah, thanks again, Ashwin. And so just let you know, I think there is 18,500 audience online. But unfortunately, they are not able to ask a question. So probably they can send you an email if anyone does have some specific question. So next, Ashwin, you can take a break, and I will go back to share my screen and bring up all the panelists. So let me introduce the three panelists we have for today. I don't see the screen switching from the online, but anyway, I think I'm going to go ahead. So let me introduce our first panelist. It's Professor Xin Zhou. So Xin Zhou is an associate professor at the College for Intelligent Science and Technology in National University of Defense Technology. He also received a PhD degree from National University of Defense Technology. And after that, I think he has been a visiting student at the University of Cambridge as well. And his research interest is focused on dynamics of MEMS and neutral sensors, and also has published quite many, like over 50 academic papers in the top tier journals. So welcome, Professor Shinjo. And if we move on, let me introduce our next panelist. It's Professor Hemin Zhang. So Hemin Zhang is a professor at the School of Mechanical Engineering in Northwestern Polytechnical University. He has been a postdoc at ESIEE Paris, University of Cambridge, and the KU Leuven between 2019 and 22. His research interests including MEMS resonators, couple resonator, mode localized sensors, and their conditioning circuit. So welcome, Professor Zhang. And move on to our last panelist. So because I'm not sure Professor Alice Zhang will be online. If no, so the last panelist is Professor Xudong Zhou. So Xudong Zhou is a principal investigator at the State Key Lab for Transducer Technology, Aerospace Information Research Institute, Chinese academic sense. He served as vice director of National Key Lab of Microwave Imaging Technology. Is the director of School and of Electronics and Integrated Circuit, University of Aerospace Information Technology. So Xudong received his bachelor in microelectronics from Peking University in 2009, and the PhD in mechanics, material, and design from University of Cambridge, Ashwin's group in 2013. His main research interests including the integrated micro and nano electrical mechanical system with a focus on resonator and neutral sensors, including design optimization for high resolution MEMS resonator neutral sensors, and also studying some nonlinear effect on the noise processing MEMS oscillator. He also worked on some sensor fusion technologies, such as slime whale using MEMS sensors for autonomous navigation and distributed pet application. And also Xudong served as the junior vice director for Transducer and Microsystem Society in CIE, the committee member of Micro Nano Transducer Technology Society in CSMNT, and also the TPC member of HV Initial Conference since 2024. Okay, so welcome, Xudong. So now I think we should all be able to on the stage. Okay, I don't see a switch. But anyway, I think we can start some panelist discussion. So welcome, everyone. Yeah.
Hold on.
Yeah, I think the screen should switch and bring everyone's, the face on the stage.
Okay, so it's already now, or seems it's not appeared now.
Yes, I think yeah, now it's ready. I think everyone, if you look at online the page, they can see everyone
okay.
on the stage. Yeah.
All right, great.
Okay, so let's start it. I think it could be the freestyle. It doesn't have to go to one by one. So if any one of you, the three panelists, I think you can start some discussion. Yeah. Who won't go
Right.
first?
Okay. Okay. I go first anyway. Okay. Thanks, Professor Lu, and hi, Ashwin. Very glad to see you online again. It's been a while. I think we last met 2 years ago in Cambridge, and it's glad to hear that you now move to India as well. So yeah, so well, for us, I think, yeah, so it's a familiar area, but I have several questions. So let's start from the first one. So how do you think the next move step of this field? For example, you recently published a paper, NC1 with He Ming, and it's talking about energy transfer between the coupled resonators. So, and I also read some papers about using the coupled MEMS resonator or even NEMS one to build up like a quantum bit for the quantum computation. So, do you think it's a promising way to develop for the next um, applications for the micro nano size resonators? So, what do you think?
Yeah, no, thanks, Shilong, and it's good to reconnect. You know, and I think you also been doing some very interesting work in reservoir computing and other areas. So I've sort of been following some of the work on mode localization as well. So it's great to see. I think one of the exciting aspects of this area is that even though as a sort of a basic platform, this field has been around for a while, there is so much more to explore. So in a way, the technology base is now more mature, and we're starting to see, the ability to look at, interesting device applications. Look at exploratory work to start out with in understanding the behavior of these under different conditions. So you can think about that in different ways. Maybe under different environments, pushing limits. In different directions in those environments, looking at the sort of the whole variety of dynamics that you can explore with coupled systems, nonlinear effects, noisy dynamics, the whole set that you can explore there. You are looking at, probing the limits of miniaturization. There are new materials as well that are gaining some interest and traction for different, perhaps application scenarios, but otherwise also more from an exploratory interest. And ultimately, it would be nice to move the MEMS field to a point where we have the ability to design complex systems the same way as we design current microprocessors. So, I think for our field to grow, that leap would be very interesting. Would be a nice one to make, and I think we haven't quite found that yet. And so that's an open challenge to the community. I think there are different paradigms, not just restricted to resonators. There are other sorts of approaches that are being kicked around, for example, in terms of NEMS logic. But that's, of course, been around for a while, and there are some practical issues as well to deal with. So I think just in the sort of the resonator area and the resonance systems area, there's quite a lot to explore. If you put together, all of the different opportunities in the MEMS family, I think it's quite there's quite a lot to look at. And in terms of applications, I see there's really a lot of possibilities still. So of course, we have a technology that's fairly mature, but at the same time, applications continue to drive the technology in different directions. And we are again looking for that sort of combination of breakthroughs that might enable the next wave. So I think there isn't one answer to your question, but there's actually quite a lot that can be done, collectively in this field, which is what makes it very exciting.
Thanks, Ashwin. Thank you.
Okay, so Hemin or Zhu Xin?
Yeah. I would like to follow the Xudong's question to talk something with Ashwin. It's also but familiar for me. The contents of your presentation today. But I have something would like to know from you about your opinion from 2 points of the view. The first one is something like in the academic point of view, the trend of the resonators or the MEMS resonators or other kind of resonators, because recently I'm working on something with some high or ultra high quality factor resonators, like it's the silicon nitride or silicon carbon, to design such kind of ultra high quality factor resonators. But it seems that for that kind of materials, it's not easy to be applied to a MEMS sensor. Even we can design a kind of a high quality factor resonator, but this kind of resonator is quite difficult to be designed as a sensor. So I know there are some top groups in the top universities. They are working on such kind of ultra high quality factor resonators and using them for the some like research in the related to the quantum or something like that. So if you can give me something something about the talk about that or this is the first one from the point of view of academic. And the second question is about the commercialization of the resonator accelerometer, commercialization of the resonator accelerometer, because for now in China, a lot of institutes, they are starting to refocus on the resonator accelerometer now, and think that this is a trend of the future for the applications of high-end fields. So because you started up a company and have a lot of experience in the commercialization of the resonators, and I also would like to hear something from you about the difficulties of the commercialization of such kind of accelerometers. So that's all my questions. Thank you.
So maybe, thanks, Kevin. So maybe I can chime in for one thing, and it relates to your second question. I think the resonator become kind of the hot again for the next wave is also because iPhones start using MEMS timing, I think. I think there are 3 chips in the latest iPhone. Probably, I think that's why, especially in China, I think there are big wave. Everyone is looking to resonator. So yeah, sorry, Kevin, I just want to chime in to mention that.
Yeah, that's right.
Yeah, no, absolutely. It's great to see resonators, in commodity applications, and there's been some great work, across the community, and especially what you mentioned, resonators out of sight time have made a real impact in the timing frequency control applications. So it's great to see that sort of translation, because when I was doing my PhD, it wasn't clear at all that resonators would have that sort of commercial impact, where there's more than 1 billion of these units sold, and it was a very long journey. So it has been a very long journey for me, and it's equally a very long journey, a very tedious one, because of the fact, technological complexity that are involved, particularly as you start to push the limits, in terms of, both from a technology perspective, but also from a commercial perspective. The commercial realities are very harsh as well. And that is often not considered as an academic. You focus just on the technology, and the sort of what you consider to be the interesting questions, the typically academic science-oriented questions. But it's often in the translation, it's more the often the other aspects that make commercialization a success. And so one needs to be able to go on a learning curve and understand that, build the right teams, and work collaboratively with individuals who bring a lot of that knowledge base into that that approach. But it is a very long road for this technology, for sure. And I think if we think about a lot of what we have today, even with some of the other technologies that we take for granted, often there has been often similar sorts of significant efforts that have had to go in to make that all possible. Now, to get to the more academic question that you raised, Hemin, in terms of other materials like silicon nitride and silicon carbide. So these are excellent candidates, certainly, that should be explored. And there are approaches that are being looked at, as you know, by a number of groups studying these systems. The benefits in terms of for the resonant systems community is, as you said, one of the key benefits is the potential for the very high quality factors that have been measured in these devices. And of course, silicon carbide has got its benefits. It's still a very difficult material to machine, but it is certainly of interest, as is diamond and some other exotic materials. These are being studied, and they will be continued to be studied. Whether they ultimately translate, that's a completely different question. But I think they should certainly receive the academic interest, as you are, exploring. We're all academics first, and so we continue to be excited by these open questions. And I guess if I have left something out, you should please come back to me, and I can address your question.
Yeah, thank you.
Professor. Thank you for your excellent speech. And you are the pioneer of the resonant transducers. And we are all researchers on this field, and we are very, your work has inspired many of our following up researchers. And I have two questions I was wondering if you could give us some inspirations. The first is, as you see, the resonance sensors, the early state resonance sensors are based on single degrees of freedom. And recently there has a trend in incorporating more modes, the coupled arrays. And I was wondering, how do you think the precision limit of the system, comparing the single degree of freedom system and the coupled mode system, which one do you think has the highest precision limit? And I also have another question is about the scale, the size of the device. As you see, there are some other groups that are doing nanomechanical resonators. And I was wondering, is our what is the precision limit of, compared to the nanoscale devices to our micro scale devices, how do you think which one would have the highest, higher precision limit? Thank you. This is the two questions. Thank you.
Oh, thank you very much. I think those are excellent questions. And yeah, I mean, take the second one first. I think, certainly, as you've seen in terms of sensitivity, the nanoscale devices, of course, are much more sensitive. That is just physical scaling. But, you have to consider when you build into a practical device, there are a number of other aspects that need to be considered holistically from a system point of view. And so, for example, you may be concerned about, for example, the dynamic range, just to take another sort of metric. And you will find that there is a space for transducers operating in different domains, at different length scales that could address, different ranges. Of course, it gets progressively harder to interface to these systems as they scale down. And so there are limitations with the surrounding instrumentation that need to be addressed. That is not to say that they can't be addressed, but there are approaches now, for example, that are emerging, so optomechanical transduction techniques and so forth, that are very interesting. So I think there is certainly an assessment that will have to be done, a holistic assessment if you're looking at it from an application point of view, but certainly lots of benefits to be gained in terms of system scaling. And certain applications you may not just require very high sensitivity, maybe combined with a fast measurement response time, and you may not be worried about dynamic range. So that there is certainly a space there, and there is, as you pointed out, a lot of very interesting work happening in the general field of nanomechanical systems. So that's to try and answer your second question first. And in the area of single resonators versus coupled resonators, again, I think it's not so much about which method is more sensitive. If you're looking at very different physical phenomena, then there is a potential to leverage effects that go beyond the traditional linear resonant frequency shift-based approach. Whether you look at coupled dynamics or nonlinear effects, or other interesting phenomena that can be leveraged in these sorts of systems that allow you some metric of advancement. So in the more localized sensing context, it talked about passive immunity to environmental effects that arises from that sensing principle. So that's an important element that doesn't exist in the same way with a single resonator-based approach. Similarly, there are other examples of phenomena that provide you some element of improvement. And in fact, you're working on some very exciting results, I see, that is also going to be very significantly advancing the field. So in a way, I think you can give a very nice example of how, from your own work, how this field can be advanced. So that would be, in short, my response to your questions.
Thank you, Professor.
Okay.
So yeah. I think it's the time, right? Oh, I have one very short question. So it's also for Professor Lu as well, because I think talking about the new materials for the MEMS or even the resonators, the piezoelectric materials must be the most popular one, and I think you also do that. So my short question is that, how do you think the electrical the piezoelectric materials using for like the MEMS filter or MEMS oscillator, and maybe in future for the MEMS resonant sensors? So what's the difference? So what's the key point? I mean, the difference between the piezo MEMS for filter is also a resonant as well, but what the main difference between for the filter and for the sensor? So what do you think?
Maybe I also can add on something. So Ashwin, because a lot of people also reach out to me because MEMS timing, the set time getting popular. And but I think for filter, I mean, there's already I-bar and so, right? But also for timing, I think they always need a very high Q. But as I know, maybe Q could be challenging for piezoelectric resonator. Just to add on what Xudong mentioned, and also want to see what do you think about this? Yeah.
Yeah, so I think what we've seen in terms of timing is that you're trying to really push stability limits, right? And of course, that comes about due to a number of different factors that impact that. One of that has to do with the quality of the material. And so certainly single crystal silicon has a very significant advantage if it's processed the right way. But of course, there are other materials that could, in theory, compete. And that remains an area of exploration. I think with piezoelectric materials, I think there are very significant benefits, in terms of integration that is now pretty standard in terms of, the very high electromechanical coupling compared to capacitive in just plain silicon structures. And, there is a different space for that, where you're not really pushing, for example, Qs. So for example, in filter applications, that's not, the primary driver, and you get adequate Qs there. And really, there are other metrics that are driving that sort of, sort of research. So that it's for the foreseeable future. Certainly, piezoelectrics is doing very well, continues to do well, and beyond that, are there other approaches that are going to emerge from a filter perspective? I don't see in the immediate future, but yeah, I think this is something that continues to be an open question. So hopefully our community continues to come up with innovative solutions to the challenges that are posed. So I'll pass it on to you, Yipeng, for your response, because I think it was a question to both of us.
I mean, not really a question for me, I think, but he does. You don't imagine that I'm doing the piezoelectric material and MEMS, yeah. So yeah, I also trying to, because mostly I'm doing the transducers. What I do is low Q device actually. We want the bandwidth higher. So the first thing I'm thinking about the timing resonator is as you mentioned, Ashwin. So the material probably there are some limitation for the Q, the material loss, not as good as single crystal silicon. Also maybe the contact, there are always some contact loss also. Yeah. But maybe because quite many people ask me if I can do piezoelectric timing device for them. As I so far I don't know how to do, but maybe I will assign this project to one student, ask them to look into that. Yeah. Okay, I think the time is almost there. But anyone has more question for Ashwin? If no, I think we can pretty much close it. But I want to remind everyone, MEMS 26. So also for everyone online, we should try prepare abstract as early as possible. Yeah.
Of course. Yeah. Thank you.
Yeah.
Yeah, and
Okay.
yeah, then yeah, we can see you again on the conference.
Are you going to
that is
transduce
great.
Ashwin? Yeah. Are you going to transduce Okay.
Yeah, hoping to. So yeah, hope to see many of you there if you'll be there as well.
Mm-hmm. Yeah. Hope we can go and see you there. Yeah.
That'll be great. Yeah.
Yeah. Okay.
All right.
We can close at here. Yeah. Thanks again.
Yes.
Oh, I think 1 minute. I think there is one there is the digital plug for you. I think I don't know, maybe Alice has a paper one they will mail it to you, but this is a digital plug for you to give a talk for the IX talk. Yeah, thank you. Thank you, Ashwin. So
thank you very much.
Yeah.
Thank you all.
Thank you. Bye.
Yep.
I don't think
thank you.
But I think they asked me to promote for the next talk, but I don't see the online sharing go to my screen, so probably you can forget about that. Yeah. Okay. Yeah. Thank you,
Okay.
Ashwin. See you.
Yeah.
All right.
Thank you.
Yeah. Bye-bye.
See you. Bye.
Yeah.
Bye.
Yeah, take care. Bye.
Bye, everyone.
Bye-bye.
Goodbye.
Take care. Bye-bye.
Bye.
Bye-bye.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心